Right, I'm back again. I have an object on an inclined plane, and the inclined angle is 30 degrees, right? And the, the object is also being pulled at an angle. The string and the string is a tension of T, and the object actually is moving down. No applied force, there's no applied force downward, but it's moving down, and there's friction, right? Now, to be able to help us, this is my problem that I think we must be well explained. We want to be able to identify an expression for the work done, one-term expression for the work done by gravity. Okay, then we want an expression for the work done by friction. We want to discuss the work done by that opposing force, the tension, because the object is moving downwards, right? So obviously, whatever is making it move downwards is doing positive work, although we know that work is not effective. But I want us to be able to get the one-term expressions for this. And the other thing I want an expression for the normal force, right? Because sometimes we have to use it to get the frictional force. Okay, so let's get started. Right, let's start with if we want to do to calculate the work done by the gravity. Oh, so we need also, let's say the displacement is delta x. So it moves downwards, right? And the displacement, we are just going to call it distance. Because no work is done with an object. It remains stationary, remember? Okay. So work done by gravity is always working vertically downwards. Right. So which force is actually contributing to the work done by gravity? Anyone? Yes, brilliant. So it is the work done by the component of the parallel component of gravity. So work done by FG parallel. Very good. So let's write it down. It's the first thing there. We're going to be work done by gravitational force is going to be mg sine theta. Let's write quick so that we don't waste time. Times delta x. Right? Now that delta x is lined up in the same direction as the displacement. So we are going to use cos, yes, times cos of theta. Very good. Right, that's the positive work done. Then work done by, next one, work done by friction. So if we know it will be the frictional force times the displacement, delta x, yes, times, how do we make, what angle does the friction make with the direction of the 180? Yes, correct. So it will be times cos of 180 degrees. Right. Okay, so that's work done by, that will give you -1. When you calculate that, that cos of 0 is 1, so this is positive, this will be negative work. Okay, so work done by the tension, by that force, right? What should we do? Yes, we use the component of the tension here, which is also parallel to this, but at 180 degrees. So it will be tension cos, that angle is 20 degrees, cos 20. Tension cos 20 right? Then the angle that it makes is 818, so it's also cos 180, which means it's also doing, sorry, I forgot to put the delta x there, times the delta x. So which means it's actually better to put delta x first, because the problem of numbers, t cos 20 times delta x. Because if I put delta x is the number, if you put it after the 20 there, some learners struggle there. But it's actually t cos 20 delta x. Then multiply this by cos 180 degrees. Right. That will give you the work done. It will be also negative work. So you will be asked work done by the net. Well, let's do an expression for the friction first. Friction is, if you are given the coefficient of static or for friction, then it's the coefficient of static friction times the normal force. But the normal force itself in this situation would be the mg, what is it? Mg, yes, you're right, mg cos 30, right? But it's pulling up, right? Is that all? No, no. So what is? Yes, minus t sine 20. Remember, I think now we know we've explained how we get to this. And by now we just apply what we did. So mg cos 30 minus t sine 20. You can just substitute it there to get your frictional force. Good. So what else? Work net. If you are given the initial the velocities, yeah, there are three ways of calculating work net here. So it depends what you are given. If it depends on what you are given, you can just calculate the change in kinetic energy of the object. That's one super method, right? If the velocity is moving constantly, with constant velocity, to be half mv squared minus half mv squared, you change in kinetic energy, and so therefore the net weight done will be zero. And in any case, if something moves with constant velocity, the net force is there. So another method to use is where you say work net. I'm trying to check where the space work net is equals to the net force, if you can get it, which is forces down, which is mg sine 30 minus all the forces going that way, minus friction minus t cos 20 gives you your net force. Then you multiply that by delta x. Yeah. Then obviously your net force is in the same direction as the movement of the object. Then they say cos 0. Hope we have got this. The third way of calculating net force would be to sum. You can use this after having done that. You can say work net. Let me do it here. Work net, the third way, would be equal to your positive work, which is work done by gravitational force, in this case, work done by mg sine theta, plus, but it will be minus, this will be negative values, minus the work done by friction, minus the work done by the net force is just adding. We are just adding, guys. So I'm using plus, but this will be minus. This will be minus when you put the values. This is negative because you know that work is not a vector, but you can say something is doing negative work, and some other force is doing positive work. That's it, right? Plus work done by friction plus work done by tension. But these two, because net is always sum. Anything with the word net, we'll ask to define it, just say sum. Done. Thank you so much. Please don't forget to comment, subscribe, give me likes. We want this world to develop to the extent that life becomes comfortable for everyone. Thank you.